All right, welcome to video 2.4. We're going to think about how elements or atoms of those elements can combine to form compounds or molecules in this case, and how we can differentiate those compounds based on the type of bond that forms. We'll talk a lot about bonding in this class in later weeks, but we're going to give you sort of a general premise for the difference between a covalent bond and an ionic bond. So in general, this sort of decision tree that I have here subcategorizes matter into either a mixture or into pure substances. And so pure substances can be the elements that we've talked about before, so the 118 odd elements that form the basis of the periodic table that we have here, or combinations of those elements when they combine through laws of definite and multiple proportions to form these chemical compounds. Those are through distinct bonds. So they're actually connected to each other through these two different types of bonds. And so the big difference here in matter is either you have pure substances, which either can be individual elements on this table or combinations of those elements, but in any case, those are bound to each other, or we can have mixtures. And mixtures are when you have multiple elements or compounds, but they're not bound together. They're just collected in the same space with each other. Okay, so when we're thinking about bonds, in this class, we'll primarily focus on these two general types, the covalent type and the ionic type, and I'm going to talk about them each in order, starting with the covalent bond. So a covalent bond is one in which electrons are shared between atoms. These are typically formed between nonmetals or semimetals on the periodic table. So this colored region to the right, often when these things are bound to each other, they form a covalent type bond where electrons are shared between those. An example of a covalent type bond would be any one of these types of molecules that I have represented in this figure here. There's a handful of different ways to represent molecules, and we're going to talk about a lot of them, so I want to just give you a flavor. You don't have to be an expert yet, but you'll see these represented in your book and in my mini lectures in different ways. And so one way is to be really explicit about the bond, in which case we have this sort of ball and stick model. This is really common if you go on to take organic chemistry like Chem 250 or Chem 251. This is a common way to represent the molecules. The benefit of this is it's really clear where the bond exists between two atoms. Here in this example we have hydrogen chloride, which we also call hydrochloric acid. We have the small white atom as hydrogen and the larger green atom as the chlorine, and they're joined together by sharing two electrons between themselves, and that's the covalent bond that exists between them. So this is the ball and stick model. You can see the same thing. This is water here, H2O. It's got this characteristic bent shape, which we'll talk a lot about in this class. Ammonia, it's got this shape, sort of looks like a pyramid, and then we have methane that looks like this tetrahedron. But in each case in the ball and stick, the bond is really clear. The same exact molecules can be represented in these space-filling models. So they're exactly the same, except the bond is no longer explicit. You can infer where the bond is just based on where the two colored atoms meet each other in space. The utility in representing the space-filling model is that it really gives you a sense for the shape of these molecules in reality, because if we take, for example, methane, in reality the molecule would look more like this at the molecular level than like this, but it's maybe easier for us to recognize shape and function when we're explicit about the bonds. Okay, so these are different ways to represent sort of the structures of the same molecule. We can write it out using their chemical symbols like this, which is common when we're balancing and writing reactions. We can write it in space-filling models to give us a sense for the actual true shape of the molecule, or we can be clear about where those bonds are using ball and stick. Each has its own benefit and utility for representing different molecules. Okay, so we can contrast the covalent bond with its distant cousin here, the ionic bond. The ionic bond is also just as common, but is very different in both its strength and its nature. And so if we talk about covalent bonds as, say, an HCl molecule where you had two electrons shared between those two atoms sort of equally, you can imagine this sort of as a tug of war on a rope where both atom is equally pulling those electrons towards itself, and the bond is the tautness of the rope that's held between those two atoms. An ionic bond is very different in that this is when the electrons are not shared, but instead one electron is transferred from one of the atoms completely to the other. And so in this case, so for covalent bonds, we said typically those are formed between nonmetals. So for example, we could have nitrogen and oxygen form nitrous oxide. That would be a covalent bond where the electrons are shared between the two atoms. In an ionic bond, though, we're typically forming bonds between a metal. Remember, metals are this big gray group here. So we're forming a bond between the metals and the nonmetals. And so typically metals like to give up an electron, and metals coincidentally like to accept them. And that sort of forms the foundation of what an ionic bond is. And we'll talk a lot about bonding later in this class and why metals tend to give them up and nonmetals don't. But that's the general sort of rule for how ionic bonds are formed. Let's think about an example here of the formation of sodium chloride or table salt. So if we had pure sodium metal, and I'll write this as a solid, plus, and I'll balance this as chlorine gas. So we've got, in this case, the metal in the sodium, and we have this non-metal, which is the chlorine gas. Right, chlorine's all the way over here, sodium is over here. These two things can combine. This is actually the industrial way table salt is made. And sodium, which started as a neutral solid atom, is going to give up an electron. Remember, electrons are negatively 1 charged, which means this is going to give it up and it's going to become positively 1 charged because it's missing that electron. That electron is going to get transferred over to these chlorine atoms, and so what we're going to be left with is chloride because it has now the electron that sodium got rid of. And so that's exactly what happened in this ionic bond. The sodium transferred one of its electrons over to chlorine, and so what we yield from this are these two ions. We call these ions instead of atoms because they have a charge. So an atom is neutral. Its constituent ion is with the addition or subtraction of an electron, which makes it charged. And so what we actually get is sodium chloride solid, and now these things are being held together simply by the electrostatic interaction between a positive and negative object. Right? So you've got these balls that are positively charged, and then you've got these other balls that are negatively charged, and they form what we colloquially think of as table salt, positive and negative charges. This interaction, there's no longer any shared electrons. There's been complete donation over to one, but they still have a positive and negative attraction, and we call that the ionic bond, which is distinctly different. So ionic bonds are typically between metals and nonmetals, which is in contrast to covalent bonds, which is just simply the nonmetals. Okay, so we just talked about how ions are just charged atoms, meaning they either have the absence or the presence of an extra electron, which gives them either a positive or a negative charge. And we talked about things like sodium plus, that was after it lost an electron. That is the ion form of sodium. And then Cl minus is the after chlorine atom has gained that electron, and we call this the chloride ion of chlorine. And so we call these monoatomic ions because it's really just one atom that defines the ion. But we can also have multiple atoms bound together to form a new compound, but that new compound still has a charge. We call those polyatomic ions, and they're really, really common. In that case, you have a variety of atoms that are bound together covalently, but the overall charge on that covalent compound is charged, so we call that a polyatomic ion. In other words, all of these polyatomic ions that are in this table that I'm showing you here, these are all covalent compounds, meaning the bonds that form, say for this ammonium ion, in this ball stick nomenclature, these are shared electrons between the nitrogen and the hydrogen, and there are 4 bonds that form. But overall, this entire compound has a positive 1 charge, which means we call this still an ion, but we call it a polyatomic ion because it contains more than 1 atom. And so for this class, and really in chemistry in general, we use polyatomics all the time. And so I'm going to go through and highlight the ones that I want you to know for this class that I won't give you this handout for. So I want you to know ammonium, I want you to know carbonate, I want you to know, let's see, nitrate, nitrite, phosphate, and sulfate. So it would be really helpful if you could commit to memory. I don't like to commit a lot of things to memory, but these just come up so frequently that it's worth your time to not have to look these up. If you could look at these 6 polyatomics and just commit them to memory, these are really common. Okay, so once you have polyatomic ions like this, then you can form ionic compounds or ionic bonds between these individual ions. So for example, actually there's another ion that I want you to know that's not listed here. Oh yeah, here it is, hydroxide. I want you to also know this one, OH minus. Okay, so these polyatomics can then bond with other charged species to make ionic compounds, just like sodium and chloride could come together. So we could have that ammonium compound, which is this one here. So ammonium, I could write as NH4 plus. That's the same as what I have drawn here in the line bond structure, and that could bind with anything that has a negative charge to it. And so, for instance, that could bind to chloride. So we could have these two come together to form ammonium chloride, where the ammonium here is a polyatomic ion. And remember, that polyatomic ion itself is bound covalently. So all of these bonds inside of the ammonium ion are covalently bound, but collectively this ion has a positive charge and it's going to bind to this negative charge electrostatically to form an ionic bond. Right, and so we could have any version of combinations of these. We could have ammonium plus, and then we could grab, say, this hydroxide ion, which is OH minus. So these two things could come together and they could give us ammonium hydroxide. Again, this molecule is covalently bound internally. This molecule is also covalently bound internally. They can combine together to form this new ionic bond. This could be true for, let's just do another example. Let's say this nitrate example here. So nitrate is NO3 minus. We could combine that with, say, just a monoatomic ion like magnesium. In this case, this is a 2+ charge. This is a -1 charge, which means we're going to need 2 of these for every one of these, which is going to give us this magnesium, and then I'm going to put in parentheses the nitrate and then a subscript 2 down below. This subscript 2 indicates that I have 2 of these nitrate polyatomics for every 1 of the magnesium. It's really important that all ionic compounds that we form, they will always add up to a neutral charge. We can never have a positive or negative ionic compound. They will always combine in whatever proportion is required to neutralize each other. So these are neutralized or neutral in their solid state. Okay, so that is ionic bonds formed from polyatomics. Okay, so let's do a couple examples and just look at some compounds that I have listed over here in blue. And let's make some sort of hypothesis as to whether or not the bonds formed amongst these compounds are actually ionic or covalent in nature. And so let's look at this first one. This is BaF2 barium difluoride, and let's evaluate what we think the bond type to be. So remember, for covalent type bonds, those are typically nonmetals bound to each other. So these colored compounds bond to each other. It's important to note that in this representation, hydrogen here is colored, right? And the key tells us that hydrogen actually behaves more like a nonmetal, even though it's located on this side of the periodic table. And so it's a little bit of an anomaly, and we'll talk a little bit about hydrogen more in this class, in that it sometimes behaves as both, but we're often going to think about it more as a nonmetal. So when we see hydrogen bound, we're going to consider it a nonmetal. Okay, so for barium fluoride here, let's find barium. Barium is all the way over here. And we find that in group 2A, we know that to be an alkaline earth metal. This is part of the metal category. And then fluorine is all the way over here. And so fluorine is in the nonmetal group. So we've got a metal plus a nonmetal. We're going to call that an ionic type bond. Let's look at SF4. In this case, we've got sulfur here, fluorine here, both nonmetals. So this is going to be considered a covalent type bond. pH3 or phosgene gas. This is essentially mustard gas that was used in World War I. We've got phosphorus here. Hydrogen is all the way over here, but remember, we're going to treat this as a nonmetal. So that's nonmetal plus nonmetal. This is, again, another covalent type bond. And then we've got this compound, CH3OH. This is methanol. So you may have seen this. This is one carbon short of ethanol, which is what people use to sanitize and to drink. So we have carbon, hydrogen, oxygen, and hydrogen again. So we've got carbon, oxygen, and hydrogen. We have all nonmetals. This is a completely covalent compound by nature.